Today, we are diving headfirst into the inferno. We're going to uncover a process that's, and I'm not kidding, absolutely essential to our modern world, but most of us never get to see it. We're talking about pyrometallurgy, the ancient and fiery art of forging pure, strong metal from nothing more than a simple rock.
I mean, really think about that for a second. How do we get the steel for our bridges, the copper for our wires, and the aluminum for our cans from a simple rock? It all comes down to this one huge question. The answer? Well, it's a mix of some serious chemistry, incredible engineering, and just a whole lot of heat. So let's get into it and uncover the secrets of this amazing transformation. All right, so here's our game plan. First, we're going to cover the absolute basics. Then, we'll see how everything separates when it gets incredibly hot. After that, we'll look at the chemical recipe that makes it all work, check out the massive industrial gear they use, and finally, see how they manage to control this, well, inferno.
Okay, first things first, let's get a handle on what we're actually talking about. What in the world is pyrometallurgy? You know, the name kind of gives it away. Pyro for fire, and metallurgy for the science of metals. Put simply, pyrometallurgy is trial by fire. It's all about using extreme temperatures. We're talking thousands of degrees here, to literally force the elements in a rock, in an ore, to break their chemical bonds and rearrange themselves. And when they do that, the metal you actually want is finally set free.
Now, when you heat up all this rock, it doesn't just turn into one big, messy puddle. No, it's way cooler than that. It actually separates into these really distinct layers, kind of like when you mix oil and water. So let's take a look at the ingredients inside this massive molten soup. Inside that furnace, you end up with these three key liquid layers. Way down at the bottom, because it's the heaviest, is your pure molten metal. That's the prize, right? Now, floating on top of that, you might have a layer called matte, which is full of metal sulfides. And then on the very top, you have a layer called slag. It's a perfect demonstration of a basic principle. Density is king. The heaviest stuff always sinks to the bottom. You might hear the word slag and just think, oh, that's just waste. But it is so much more than that. It is the unsung hero of this whole process. Think of it like a chemical sponge. By tweaking its chemistry just right, metallurgists use the slag to actively pull all the junk, impurities like silicon or phosphorus, right out of the molten metal, leaving it clean. Here's the key takeaway. Without good slag, you just don't get pure metal. So we have our ingredients all separated out, but how do we actually cook them to get what we want? Well, it all comes down to a really fundamental chemical recipe. You can really think of it in 3 simple steps. First, you've got to prep the ore. This is kind of like chopping up your vegetables before you cook. You're just getting it into a more useful chemical state, usually turning it into an oxide. Step 2 is the main event, extraction. This is where you use something else, usually carbon, to literally steal the oxygen away from the metal. And finally, step 3 is refining. That's the last cleanup job, just getting rid of any lingering impurities to get the metal to the exact purity you're looking for. Okay, don't let this chart freak you out. You don't need to read a single number on here, I promise. This is called an Ellingham diagram, and all it shows us is something really simple. Who wants oxygen more? Think of it like a giant game of tug of war for oxygen atoms. And the rule is simple. The line that's lower on the chart wins. So just look where that thick black carbon line drops below the iron line. At any temperature past that point, to the right, carbon is going to win that tug of war every single time. It'll rip the oxygen right off the iron ore, and that leaves us with pure iron. That right there, that's the secret sauce of making steel. All right, so we know the recipe, but what kind of kitchen can actually handle this level of cooking? We are talking about some of the biggest, most powerful, most impressive machines on the face of the earth. On the screen here, you can see 2 absolute titans of the industry. On the left, that's the classic iron-making blast furnace. It's this huge tower where they feed ore and a special type of coal called coke in the top, and then blast superheated air in through the bottom. And on the right, you've got a more modern electric arc furnace. Instead of burning fuel, this beast uses these enormous graphite electrodes to create an electric arc, a plasma that is literally hotter than the surface of the sun to melt down steel. 2 very different tools for a very similar and very, very hot job. And this, of course, brings up a pretty obvious question, right? If you're containing a liquid that's 3,000 degrees, what in the world are you containing it in? How does the container not just melt? The answer is a class of materials called refractories. These things are incredible. They are the ceramic supermaterials that make any of this possible. They are literally designed to do the impossible, stay solid while holding a liquid hot enough to vaporize just about anything else. They not only have to survive the insane heat, but they also have to resist being chemically eaten away by the slag and handle the physical stress of holding all those tons of molten metal. And getting all that heat into the furnace is a whole science in itself. You can do it the old-fashioned way by burning fuels like coke or natural gas. You can use massive amounts of electricity, like in that arc furnace we just saw. Sometimes the chemical reactions are so energetic they actually produce their own heat, which is pretty wild. And to be super efficient about it, they use heat exchangers to grab all that waste heat from the hot exhaust gas and use it to preheat the air going in. It's all about recycling as much energy as you possibly can. So we've basically created a controlled volcano. Now, how do you manage everything that comes out of it? Not just the valuable metal, but all the other byproducts too.
This is a massive part of modern pyrometallurgy. You can't just let all those super hot, dirty gases vent straight into the atmosphere. This whole system is basically a giant air purification plant. First, the gases go through a system to cool them down and recover some of that waste heat. Then they hit electrostatic precipitators, which use a huge static charge to pull all the dust out of the gas so it can be recycled. And finally, the gas is scrubbed to remove pollutants like sulfur dioxide before it's clean enough to be safely released. And after all of that, all the preparation, the chemistry, the incredible heat, and all that control, here it is, the grand prize. This is a ladle just brimming with molten steel, glowing at over 3,000 degrees Fahrenheit. This is the culmination of everything, rock transformed by fire and by science into the pure, liquid heart of our entire infrastructure, ready to be cast and shaped into the world around us.
Think about it. Pyrometallurgy has been with us for thousands of years, evolving from ancient blacksmith forges to the hyper-efficient industrial giants we have today. It gave us the Iron Age, it powered the Industrial Revolution, and it built our modern skylines. As we look to the future, for new materials and more sustainable ways to build everything, it really makes you wonder, what new fiery art will we need to master and what will we forge next?